So, welcome back. We're in the midst of working through the part of the course having to do with how to write down dynamics. And this intermediate part of that section is about chemical transformation. So, in the last vignette, we talked about ligand receptor binding. And what I want to do now is I want to give you the canonical view of the dynamics of enzymes, although it's a much bigger subject than what I will say. So, maybe later we'll have a chance to talk about enzymes which have some sort of feedback, sometimes in the form of allosteric, sometimes in the form of inhibitor molecules, and so on. For the moment, what I'm going to do is give you, in a certain sense, the sort of simplest version. And this goes under the name, for our purposes, of Michaelis-Menten Kinetics. And the idea is really kind of simple, which is that we have some enzyme, which I'm going to schematize here like this. It's got some active site. Plus, we have a substrate, which I will schematize as this dumbbell-shaped object. And enzyme plus substrate goes with a forward rate, which I'll call K plus, and a backward rate, which I'll call K minus, to the enzyme substrate complex, which looks like, copy, which looks like this. And then at a rate constant, which I will call R, it goes to enzyme plus product, and that looks like enzyme again, and then plus the two guys which have now been cleaved. So that's the reaction that we have in mind, and in a certain sense, the whole topic hinges on the rate at which we make enzyme substrate complex. So first thing we're going to do is we're going to write down the dynamics of product formation. And that we will do using exactly the same sort of rate equation mentality that we've already introduced. So maybe I'll say the number of product, how do I want to write it? Maybe I'll say the product at time t plus delta t is equal to the number of product molecules that there were at time t, and then plus r delta t, and times ES, where that's the number of enzyme substrate complexes there are. So this thing can be rewritten as P of t plus delta t minus P of t divided by delta t, which I'm going to just cut right to the chase, is dP by dt, and that's R, and then times the concentration of ES. So that's our equation for product formation. So this is the dynamics of product formation. And just because I want to simplify things, I'm going to rewrite this as R and then times E tot, and then multiplied by ES over E tot. And this thing I'm going to give a name, which is Vmax. Why would I do that? Because the fastest that I could make product is if every single one of the enzymes that's present is cranking out product at a rate R. That's the fastest that I could produce product in this scenario. So we can rewrite this as Vmax and then times ES over E plus ES, since this denominator is E tot, right? The total amount of enzyme is the enzyme that's free plus the enzyme that's complexed with substrate. So that's the total amount of enzyme. So that's what we have to say about the equation for dP by dt. Now let's write down the equation of motion for ES. So this thing is going to increase at rate k plus proportional to E times S. So this is just like we did for ligand receptor binding. It's literally the same thing. We have the second order reaction. And then we're going to subtract off from that minus KES. But also we're going to subtract off minus RES. So let's just annotate these things. So this is the rate of complex formation. And this guy is the rate of complex disassembly. And then finally, this piece is the rate of product formation. And the thing that you're supposed to carry away from this is that there are two ways to exit the enzyme substrate complex. Either we could disassemble and go back to the free E and S, or we can become product. And in that case, it's no longer ES either because the substrate has been released. So that's the full picture. Now, here comes the big assumption. So assumption. And that is that the ES reactions are sufficiently fast to be in steady state. If that's the case, then from this equation above, what we have is this whole thing is equal to 0. And I can recast that nicely as telling me that ES is equal to K plus over K minus plus R times E times S. That's fantastic. So we got this nice simple relationship between the ES concentration and the free E and free S. So now the plan is we're going to take this and substitute it into the equation for dP by dt. Let me go up and copy that equation and bring it down. So copy. So I know that dP by dt is equal to this thing, and if I substitute here and on the top, what I get is I get E times S over Km over E plus E times S over Km, which is equal to, and there's a Vmax out in front, which is equal to Vmax, and then times substrate over Km over 1 plus substrate over Km. So that's really fantastic because, and by the way, I should mention that I've defined Km, which is defined as the Michaelis Constant. And that's equal to K minus plus R over K plus. The units here are, K plus has units of inverse molars inverse seconds. K minus and R have units of 1 over seconds. So the net units are molar concentration. So the interpretation here is the Michaelis constant is the concentration of substrate at which we get half maximal activity. So that's the picture. Let's actually just take a look. So first of all, this is the summary of what I've just told you. So basically the maximum reaction rate is this V max, and the Michaelis constant tells us where we get half maximal rate. This is kind of fun. What I'm showing you here is what would happen if you actually solved those equations, and what I guess I want to say is that the time scale over which product is formed is much slower. Um, let's see, how do I want to say this? Yeah, so um, okay, first of all, what are we doing? We're plotting the substrate, the enzyme substrate, and the product as a function of time. Time is scaled in units of k minus plus r inverse. So remember, k minus has units of 1 over time, so 1 over k minus has units of time. So there's a time scale there. And what we're seeing is that after this initial transient, the substrate, which you see in red over here, the substrate is slowly bled off. And yeah, I guess that's the key points I wanted to make. And here I show you a plot. It's basically a linear plot like the one we had a little while ago that tells us the rate at which the reaction is taking place as a function of the concentration of substrate, and as advertised, when the concentration is Km, we get half maximal rate. If I remember correctly, these dots actually correspond to data for a particular enzyme, and I apologize, but I forgot which one. That's the case here as well. This is fraction converted. I think those are the key things that I wanted to say in this vignette.